So welcome to the deep learning practical session. So here we are going to see how we are going to complete this lab sheet 2. So in this activity, so we are going to understand how this simple multi-layer perceptron network is actually working. So that means we are mainly focusing on the forward propagation and backward propagation. So we have discussed the theories related to that, how we are going to have the forward propagation. So that means how the network is going to pass inputs to the output side, and then the back propagation. So then how we are going to change, how the network is going to change the weights from outputs to the input side. So that is the back propagation. So we are going to simply see how actually we are going to implement by using the Python here. So let's see the activity. So in this one, so you can see that we are going to use the same data set that we have used in our lab sheet 1, that means the practical session 1. So in that one, actually we have used the Keras and we have implemented this network. But when you are using the Keras, actually we are using the inbuilt functions which are there in the Keras, the methods. So in that case, you might not get a clear idea how the internal things are actually happening. So therefore, in this one, we are going to develop these methods, and we are going to complete the same activity. Okay, let's move to the task. So here the first task is we need to create a Python class for MLP with customizable input size, hidden layer size, and output size. So in this activity, I'm going to use a very simple network, because in the Keras also we have used a simple network. So this will be the new network that I'm going to use. The input layer is there, output layer is there, and we will have only one hidden layer. So to understand these concepts, so if I explain this one little bit, you know that the input will comes, and after that in the hidden layer, so we are going to get the weighted sum, and after that we are going to add the bias, and then that value will be sent to an activation function. So then that output will be passed to the output layer. In the output layer also, we are going to do some kind of weighted sum calculation, and then we are going to add the bias, and then again we will have an activation function in the output layer. So that's how this network is normally working. So let's try to implement this kind of network, and then see how this forward propagation and backward propagation is working. So in this video, I am planning to implement this forward propagation part, and then next video we will see how we are going to have the back propagation part. So let's move to activity then. So here the first one is we need to create a Python class for multi-layer perceptron network. So then first we will create a Python class. So I will keep this one empty, because I need to import some packages, libraries when I am developing this one. So therefore the first we will have a class called MLP, and here we will have a default constructor to add these values, because we need to get three values here. So one is the input size, another one is hidden layer, another one is the output size. So we will get these things first. So this will be input size, and we need to get input size and hidden layer size, and then I mean to get the output side. So hidden layer size, I will name this as hidden size, and output size. So so I will make this as a function, and then so here the first thing is we need to have weights and bias. So if I go to the network that I have displayed to you, so this one, so here you can see that first we need to have weights. So here in this case so all these connections will have weights. Weights means Yeah, so how much important, that means how much important this connection. So that's how what normally the weight means. Okay, so we are going to give a weight for each of these connections. Okay, so now when you are developing a network, so very first case we need to have some initial weights. So you might remember when we were implementing the same network by using keras, so we have used the keras initializer parameter to set some initial weights for these connections. So now here also we need to have a way to add a initial weight into this network. Okay, so now let's see how we are going to do that part. So here we will define weights for each of these connections, because in this network you can see that we are having connections between the input and the first hidden layer, this one, and also we are having a weight in this part as well. So that means this will be the hidden layer, and here so this will be the output layer. So in between this also we need to add some weights, and here also in this part also we are having weights. So we will name this weights as the weights with input to hidden, and we will name these weights as the hidden to output. Okay, so likewise we will first name these weights. So I will name this one as weights from input to hidden. Okay, so now here we will use the random value here. So we will use numpy package. So first we will import this library. So we will import first we will import it, and then we will use np.random.rand function, and here we can have a kind of a matrix. So then we need to give what kind of random value that we need to have. So here in this one you can see that we are having a set of vector here. So that is that will be the input vector. The size of this input vector will be the input size, and again we are having a hidden layer here. Hidden layer also having a size. That hidden layer size is hidden size. Okay, so then we need to have a matrix here. So we need to have a matrix here with this input size and also with the hidden size. Okay, so therefore we will have it like this. So we will have input size and hidden size. So we are going to have a weight matrix by use so randomly we are assigning some values, and it will be input size and hidden size. So that will be the size of the matrix. Next we will have the other weights. So that means so here also we need to have some weights. So first I will clear this one. Okay, so now again we need to have weights in this area as well. So that means from the hidden layer to the output layer. So now we will add that part. So I'm going to copy no, so I will edit self dot so here now hidden to output. Okay, so this will be again weights. So we are having weights from hidden to output, and again so we are using the numpy library and random and the function rand function. And now the size is what? So here you can see the size is the input the hidden layer size, and this will be the output layer size. So then the matrix should be hidden to output. Okay, so then we will have hidden size and output size. So these are the initial weights we are having in this network. So we are randomly assigning a weight into these connections through these two code lines. So now not only the weight, so we know that in a network we will have two types of parameters. The first one is the weights, and the other one is what? Other one is the bias. So this one. Okay, so this will be the other one. So in here also we need to have a random value for this bias. But you might remember that we have used the, and in Keras also, bias initializer we have used to set an initial bias value to the network. So there also we have used the zeros. So we have assigned 0 value as the bias. So in this case also we have we will follow the same here, and here we will add 0 value to this bias. Okay, so we will have another variable here. So now it's not weights, okay, it's bias. Okay, so now the bias is with the layer. So here we are having bias for this layer. So this is the so this not, okay, I will delete that part. This is the input layer. So you can see that this bias is so this is for this layer. Okay, so this is the hidden layer, and this bias is for the output layer. Okay, so this is the hidden layer and this will be the output layer. So therefore we will have bias bias for hidden layer first, and we will use NP. So we are going to have zeros here, and here it will be a vector. So the size of the vector is hidden size because it's a hidden layer. And again we will have bias this is not for hidden, so this is for output layer. And here again we are using NP zeros, the initial bias will be zeros, and here it's a vector, and the size will be output size. Okay, so now we are having the initial weights and bias for this network. So let's go to the activity again. So create a Python class with annual customizable input size. Okay, so we have added this input size, hidden layer and output size as parameters. So now we can pass those values from the outside, and then add a separate method to initialize weights and bias for the network. Yes. So in this init method, so we have defined the bias and the weights that we are going to have very beginning of this network. So now we need to implement the method for the forward propagation. Okay, so now we are going to implement the forward propagation here. Okay, so what's the forward propagation? So in a simple MLP network, the forward propagation means, so we are going to have the input, and then input will go in this network, and then it will do some kind of a calculation here. So what's the calculation we are going to do here? So we are going to get the weighted sum. So that means sum of these connections. So here you can see we are getting 4 connections in this network. So we are going to get the sum of the weighted sum of these things, and then we are going to add this bias into this value. So this will be added to this weighted sum, and then that will be passed. So I will clear this one. So first we are going to get the weighted sum, this part, and then we are going to add this bias. So now we have calculated a value. Okay, so now this value will be sent to the activation function. Once we send this value to the activation function, it will produce an output. That output will be gone to the next layer. Okay, so then again in the next layer, so we are going to get some kind of a weighted sum here, and then again we are going to add the bias, and we are calculating a value. That value will be again sent to the activation function, then we will output the value. Okay, so that's how we are normally doing in a multi-layer perceptron network. So let's implement that forward propagation. So that is what the forward propagation means. Inputs will be added to this input will be fed to the network, and then the network will be send the output here. Okay, so that is the forward propagation. So the output will be outputted from this side. So now let's implement that part. So I will go here, and I'm going to have a separate method here. So that will be forward propagation. So in the forward propagation, so you can see what is the input that we are getting into the forward propagation is these inputs. Okay, so we will define these inputs as x. You can see x1, x2, x3, x4. Likewise, in our case, we are having 8 attributes. So we are going to pass these 8 attributes into our network. So now here those are x1, x2. Likewise, so we will have it as x. So then so this will have the variable x. Okay, so now x is what the forward propagation is actually getting as an input parameter, because x is the input. Okay, now the first thing is in this network, so let's move to this one. So now I will clear this part. So now in this forward propagation, the first thing we need to do is we need to calculate the weighted sum. Okay, so we need to calculate this one. So it's based on the number of inputs. You can see we are having 4 inputs in this sample network, and here we are going to get the weights from we are going to get the weighted sum by using this. We can calculate the weighted sum using these 4 connections. Okay, so now let's see how we are going to do that part. So the first thing is we need to calculate the z here. So in this network, so we are having the z means that's the weighted sum plus bias. So that's the input that we are actually getting into this hidden layer. So we will name this as hidden input. So the hidden input is we are going to calculate by using the dot function. So here what are the values we are getting? First we will get the x. So this is the x. Okay, and here that will be the input, and here we are having a weight. So now we so I think you might remember the formula that we have used. So this is the formula x1 dot w1. So this will be the so likewise we are going to add all these values, and then that will be the weighted sum of this one. So that will be one input that this neuron is actually getting. Okay, so then we are going to calculate that one. So x, so we will use the numpy dot function here, and we are going to get the dot of this x and the weights. So now we have initializer weights here. So that is the input to hidden weight, because we are going to use this one. So this weight. Okay, so this one, so we have named this as input to hidden weight. Okay, so that's a matrix we have created this here. Now we are going to add that one here. So now we can calculate the input, but when you are going to calculate this c, so that means the input, so we need to add another one. So that is the bias, because here you can see we are having a bias as well. So we need to add bias. So once we add bias, so we can get the input value. That means we can compute the input value in this neuron. So that means actually the c in this case. So now I'm going to add the bias. So this is the so this is the hidden layer bias that we have randomly added a value there. So now this will be the input for the hidden. Okay, so now we need to have the output. So now we have the hidden the input to the hidden layer. So in this case, so z is now calculated. So now this z is calculated actually. So now what we are going to do is we are going to pass this c into an activation function. So then only we are getting the output of this neuron. So that's how normal perceptron is working. Now let's see what's the activation function we need to use here. So here you can see the hidden layer. So we need to use the activation function as relu, and the output layer we need to use the activation function as sigmoid. So then let's add these two functions into our code. So let's have two functions. One is for this relu, So one is for this ReLU. So the ReLU is actually getting an input, and after that we are passing some value here. And again we are having another activation function to use in output layer, so that will be the sigmoid. So in sigmoid also we are getting an output input, and we are passing some value. So in the ReLU, so you might remember the ReLU function. So if I go here, so what's the ReLU? So the ReLU function is something like this. So that's like this. So it's going with the 0. So that means if there's any negative value, we are going to give 0, and if any positive value, we are giving that value as it is. So that's the ReLU function. So a very simple function. So that's the ReLU function. So now we are going to implement that function here. So first the ReLU. Okay, so the ReLU means what? It's going to return. So we are going to use the maximum function in this NumPy library. So we are going to we are going to return the maximum like this. So that means if you are getting a value from like x, okay, so that means the thing that the z value we are going to pass here. So once we pass the z value here, and then if it is a -1, so think that this z is a -1, so now it's a -1. So now this function is going to get the maximum from this one. Maximum means here it's 0, so it's going to pass 0. So now think this x is a positive one like this. Now the maximum is 1, so this will be pass 1. So likewise we can have a simple function for ReLU. So what the ReLU is doing, it will get the input, and if it is a positive value, then we will pass the value as it is. If it is a negative one, so then we will pass 0 as the value. So that's the ReLU. So that's very simple function. And then next one is the sigmoid function. So the sigmoid function, so we have already discussed what sigmoid function is. It's a S-curve function which comes which goes in between 0 and 1 value. So you might remember this tan h and the sigmoid is the different is both are sigmoid S-curve functions, but the sigmoid is working in between 0 and 1, but the tan h is working in between -1 and 1. So here we are using sigmoid. So in the sigmoid, so this is the function. So so if you go to the internet, you can see the function. So if I go to here and type sigmoid function, so this is the sigmoid function. So you can see 1 divided by 1 plus 1 plus. So this is we are calling as x. So if I take the Python code of this one, okay, so this will be the Python code of the sigmoid function. Okay, so I'm going to directly use that one here. So now I'm going to return this one. So this is the sigmoid function. Okay, so now we will see the output, what the output that we are going to get in this neuron. So now here, so now we have calculated the C. So now we are going to get the output. So how we are going to get the output? So we are going to pass the Z into the activation function. So in our case it will be ReLU. Okay, so we are going to pass this activation function into value into this ReLU activation function, and then we can get the output of this neuron. Okay, so now we will have the output here. So we will have this is the output of the hidden. Okay, so hidden output. So here the hidden output means what? So we are going to pass this value to the ReLU function, and what is the value? This value. So this is the hidden input. Okay, so we are going to pass this hidden input to the ReLU function. So then we are going to get the output of the hidden. So now let's move to the other side now. So now we have calculated. So I will erase these things. So now this part is already calculated, and now we have produced these outputs. So now these outputs are there. So what are the what is the output here? That's the hidden output. The output, the hidden layer is produced here. Okay, it's based on the input that we are getting. So now we need to calculate the output here. So to calculate the output here, again you can see that we are going to have a Z here. So how we are going to calculate the Z? Input. The input now, the output of this neuron, because this is the input for this neuron. The output of the hidden layer neuron will be the input for the output layer neuron. And here again we need to calculate the C. So when you are going to calculate the, how we are going to calculate the C? So we are going to get the weighted sum of these inputs, and then we are going to add this bias. So once we add this weighted sum and bias, so then we can calculate the C here. And again we are going to send this value to activation function. So in this case we are using what? Sigmoid as the activation function. Okay, so we are going to have sigmoid as the activation function. So in this case, so let's see how we are going to have that one. So that's again, so we are using the same one. So now here input for this output layer, again it's a dot matrix, it's a dot function. So now the input is what? The input is the output of the hidden layer. So this will be the output of the hidden layer, and again we need to have the dot function with the weights of this layer. So this will be the weights, hidden to output weights, and then again we need to add the bias of this one. So this is the bias of the output layer, so we are going to add that one. So now we are going to generate the final output. So here the function we are going to use, activation function, is the sigmoid. So then we are going to pass this output layer input, to the sigmoid function. So then we can return the final output. So that will be the sigmoid. That will be the final output. That means that's the output that we are getting through the forward propagation. So in this case, so that will be this value. Okay, so we are going to return this value through this function. So let's execute and see whether we have any issues here. Okay, so now these are the first few parts. So now we have completed this forward propagation, and here we need to implement a basic loss function. So in this case you might remember that during our last practical, so we have used binary cross entropy as the loss function. So I will add binary cross entropy loss function as well in this case. So here so if you go to the internet, you can get the Python code for this binary cross entropy loss function. So we will define a function here. So in this case we are getting two values. One is the what is the true value, because you know that what's the main purpose of a loss function. So we are going to have the difference between the actual and the predicted. So that is what the loss means. Okay, so the optimizer will use these loss functions to optimize the model, because based on the loss function, so we need to minimize the loss function. So that is our target. So to minimize the loss function, so we need to calculate the difference between this the y true and y pred. So the predicted value and the true value. So we need to have those two values, the y true and y pred, and then we are going to calculate. So this is how we are normally calculating. So this actually I got this from the internet, so the binary process entropy, so that's there. So you can search on the internet and you can get the Python function for this binary cross entropy. Okay, I will delete this part. So now this will be the binary cross entropy. So I will again execute and okay, so there's an indentation problem here. Okay, now it's fine. So this will be the binary cross entropy. So you can search on the internet and you can get the Python implementation for this binary cross entropy loss function, and then you can add it like this. So that will be the loss functions that we are going to use in this activity. So then now we have completed up to the fifth task. So next one is the backpropagation. So how we are going to have the backpropagation one. So so let's see that in the next video. So so I think you have got some idea about how this forward propagation is working here. It's very simple. So first we need to have the initial weights and bias in this network. So those are the parameters that the network is going to optimize or the fine tune during the training. And then we are going to calculate the forward propagation. So first we are starting from the input, and we are going to calculate the inputs that the first hidden layer is getting here. So we are using the dot function here. So the x is the input, and then we are going to pass the weights associated with this input, and then we are going to calculate the weighted sum. So once we calculate the weighted sum, so we are going to add another parameter, so that's the bias. So once we compute this value, so this value will be sent to the activation function. So in this case we are using the activation function as ReLU. So what's ReLU is doing? So ReLU is getting an input. If the input is a negative value, so then it's going to pass 0 as the output. If it is a positive value, it will pass as it is. So that is how the ReLU is working. So then that will be the output of the hidden layer, and then the input for the output layer. So that means the next layer will be the output of the previous layer. So then we are again going to use the output of the previous layer with the weights which are there in these connections, and then again we are using the dot function, and we are going to calculate the weighted sum, and again we are going to add the bias into this one, and then we can calculate the input for the output layer. So once we calculate the input for the output layer, again we are going to pass this into the activation function. So in the output layer, the activation function is sigmoid we are going to use. So then we are going to pass this value into the sigmoid. So the sigmoid is what? So the sigmoid is going to give a value in between 0 and 1. So that is the value. So this is the function we are normally using in the sigmoid. Okay, so once we apply the input into this function, so then we can get a value in between 0 and 1. So that value will be the output of this network. So then you can see in the forward propagation, actually what we are getting is the predicted value. So once we input and input a kind of a x value, that means input to the network, so then that will go through each and every neurons which are there in the network, that each and every layer which are there in the network, and then finally it will output a value. So that will be the predicted value. So now through the forward propagation, we are actually returning the predicted value for a given input. Okay, so now next video, so we will see how we are going to develop the backward propagation. So that is the next algorithm. So I told that around 1990s this backward propagation algorithm was introduced to the world, and that actually boosted up this neural network side. So in next video, let's see how we are going to have a backward propagation algorithm or the backward propagation method into this simple neural network. Okay, so thank you. Let's meet again with the next video.